Welcome students. In today's class we are going to discuss on multiprocessor scheduling. In last two classes we are discussing on scheduling on high level synthesis. So, as you remember that scheduling is something where we assign time steps to operations and it is needed because the actual initial C code is untimed. So, you do not know which operation to be scheduled in which clock. So, you have to decide that, and that is what is happening in the scheduling steps, and we have already discussed that. And in the last class we have also discussed that the ILP formulation, how we can actually model this scheduling problem as a ILP, and we have seen how to with example how those constants will be represented and all. Okay. So, and you also seen this scheduling problem is in general NP complete. Okay. So, NP complete, as you might aware that this is basically this is a complex problem, and for this there is no polynomial time. So, algorithm available, deterministic polynomial time algorithm available, right. So, you usually do not have algorithm like n order of n square n log n to solve this problem for to get the optimum results. So, you have to go for exponential algorithm n to the power k and so on, right. So, n is the number of nodes in the behavior. So, that we have already understood, and then so in today's class what I am going to discuss is we try to take a special class of this scheduling problem. Okay. And then we try to see whether that particular class is solvable, is still NP complete, or if it is not, then what is the particular subset or the subclass of this scheduling problem which is actually polynomial time solvable. Okay. And that is what is this multiprocessor scheduling is the topic. Okay. So, again you remember that the way we model our behavior. So, we have a CDFG, control and data flow graph, where we have loops and then if else branch everything, and we have actually model as a control and data flow graph, where each basic block is a straight line of code and where there is no control flow. And then the way we have discussed that we are going to take one block at a time and we model them as a sequence graph, right. So, basically it is the representation is like we break those operations into 3 address form, and then we identify the dependency among the operations, and that dependency is basically a data flow graph, and then that data flow graph we represent is basically as a sequence graph, where we put a sync node and a source node for convenient representation purpose. And in this particular this sequence graph is actually a DAG, right, direct acyclic graph. So, direct acyclic graph in the sense there is no loop, and it is understandable because there is no control flow, you have a straight line of code. So, since the code is going to happen from the top to bottom manner, so there is no back edge, right. So, there is no backward dependency because it is a forward dependencies. You might have loop and that loop will be under the control flow, but within a basic block there is no back edge. So, this is a direct acyclic graph. Okay. Now, if you just try to understand, so here I have taken various type of graphs. So, this is one graph, this is another graph, and this is another graph, and this is my source node and this is the sync node. Okay. So, you can exclude this source node sync node because they are the dummy nodes. Okay. And you can actually for this graph this is the source node and this is the sync node, this for this graph also this is the source node and this is there is a sync node. Okay. Now, let us try to understand this particular graph. So, this is our input behavior and this is what I am going to schedule, and I have seen that is basically scheduling is basically assigning time step. I am going to say this operation is going to happen in time step 1, this is going to happen in time step 2, this is going to happen in time step 3, and this is going to happen in time step 4 and so on. Okay. So, this is what scheduling does, but what is the characteristics of this particular sequence graph, right. So, if you see this graph, if you just exclude this source node or sync node, is basically it is a tree, right. So, what is the tree? Tree means if there are n number of nodes, you have n minus 1 number of edges, right, n nodes, n minus 1 number of edges, right. So, and what is the special property of the tree? It is basically you can assume that from this any node to this sync node there is exactly one path, right. If you come from this node there is exactly one path to the sync node, you take any node there is exactly one path, right. Then this is basically a tree. So, your sequence graph or the input graph can be a tree, okay, in a special circumstance, but in general it may not be. You consider this graph. So, here you consider this node, you have how many paths to this sync node? I have one path through this, I have one path through this, right. So, there are more than one path. You consider this node, from this path there are many paths, right. So, this is one possible path, this is another possible path and so on. So, this is not a tree, right, this is a graph, right. So, this is the first property. that this sequence graph in specifically can be a tree, or in general it is actually a graph. Here also there are many paths, right. So, there are, you can consider from this node to this node there are 4 into 3 into 2, which is basically there are 24 paths, right. So, this is definitely not a tree. So, this is the first thing. So, your graph in general, this drag is a acyclic graph, there is no cycle, there is no backage, but it in general it is a graph, it is not a tree, but in a very specific case it can be a tree as well. Okay. Next is we have seen that this the nodes can actually perform many operations, right. This is a performing multiplication, this is performing subtraction, this is performing plus, this performing greater than or equal to and all, right. So, these are all different type of operations, and it is understandable that in general in hardware this all more operations are not executed in the using the same module, but you can have different function units, like you have a multiplier, you have a adder, you have a divider and so on, and so this is something that means you have the operations which are of different type. Okay. So, that is one aspect. So, the one is the structure of the tree, right, so which is graph or tree, the structure of the this sequence graph, right. So, the first thing is it is a DAG, that there is no confusion. So, all are DAG, there is no cycle. Second is it can be graph or tree. Second thing is the type of nodes, right, type of operation. So, what are the distinguishing factor that I am trying to identify? The fourth is the delay of the nodes, right, delay of the nodes in the sense. So, for example, I mean we have already formulated the problem with this multiplier can have a delay of 2, this adder can be delay of 1. So, basically it is not that all operation will take same amount of time in hardware, you might have some complex operation which might take say d cycle, right. So, for example, here I am just giving a graph where actually I have just tried to show that this node say take 15 cycle, this node say take 7 cycle, this node takes say 20 cycles and so on. So, it can happen, right. So, this operation may not be only a multiplication, it may be a set of operations as well, right. So, you can represent a say complex operations using this node as well. Okay. So, so these are the characteristics of the this general sequence graph. So, if we try, so the problem is that if in general if this graph is a graph, if you have different type of operations, if you have different node have different delays, the graph the problem is actually NP complete, the scheduling problem, right. So, the scheduling problem whether it is a latency minimization under resource constraint or it is a resource minimization under latency constraint, both are NP complete problem, it is a computationally hard problem. Okay. So, if we try to assume that this particular graph has some special characteristics, that this is not a tree, or say I have the type of operation can be same, or the delay is unit. So, in that particular sub case or the substructure is this still problem is NP complete, right. So, that is something let us try to understand. Okay. So, in the multiprocessor scheduling we have certain assumptions, right. So, on these 4 parameters we assume that this particular all operation of the same type, that means there is a multiprocessor which can execute this operation. So, that means although these nodes can be plus minus multiplication division, but you can assume there is a kind of processor which can perform any operation. This can be generic purpose processor as well, right, which can do any operations. So, the first so basically what I assume that this is not there. So, all operations are of same type. So, I do not have to bother about whether it is a multiplier or divider. So, I can consider all the nodes as a same type, right, they are not different types. The second one is that this all operations have unit delay, right. So, unit delay means as I mentioned that earlier this multiplier will take 2 cycle, this adder will take 1 cycle and so on. So, I am also assuming that there is no delay constant. So, all are of delay 1. So, every operations can be executed using single clock, right. So, so multiprocessor scheduling assume these 2 constant, that I do not have to take different type of function units, since I have a single multiprocessor which can execute all type of operations, and hence I can actually consider all nodes of the same type, and also assume that this operations are of a unit delay, right. So, delay of 1. So, under these particular assumptions, let us try to formulate this problem as a ILP, because in the last class we have solved this using ILP. So, if we have these assumptions, how this constant will change, let us try to understand that. Okay. So, if you remember that this ILP formulation, we have taken a variable called xil, right. So, which is basically because what is our objective? Our objective is to identify the timestamp where this operation is going to start its execution, and that is unknown. So, I have just taken a variable this il where I varies from 1 to n representing the nodes and l representing the timestamp, which is basically 0 to lambda plus 1. So, if a operations I vi the schedule in timestamp l, then this will be 1, otherwise it will be 0, and this is what I am going to identify through ILP formulation, that I hope you understand or you remember that. So, with that assumption that you know this this formulation. So, if we take this MLRC problem where we try to minimize the latency under resource constraint, our objective function is that is basically CT, where basically it is nothing but minimize the schedule time of the last node. I think that you remember that if we schedule the last node as early as possible. So, if the timestamp schedule time of the last node is early, because of the dependencies all our other node will be executed before that, and hence this is the minimum solution. So, our objective function for this minimization of latency is that it is basically nothing but mean the start time of the last node, and we have to represent this Tn in terms of xil, because there is no Tn, which I can represent as like this, that xn l, right. This is, and this is l into this, right, summation of this l, which is basically 1 to lambda plus 1. So, this should be minimum, right. So, this is something we try to achieve. So, and what was the constant? So, the first constant was the unique start time, that although there are many variables possible for each node, we have to assume that one operation can start only once in the behavior, right. So, and that is given by this expression that we already remember that for say a node so for a node say I, so it can say if there are 4 say timestamp and this is a node say 2. So, 2 1 plus x 2 2 plus x 2 3 plus x 2 4, if I am talking about V 2, and there are say 4 timestamp. So, this must be 1. So, that means it only can schedule in one timestamp, and since here for these two assumptions that does not change anything, right. So, these two assumptions that all operations of same type and operations have unit delay has no impact on this constant. So, in general case where there is no such restriction, the constant is this, and for my case, our case where we have these two assumptions, this constant will be same, because these two assumptions does not impact on this particular constant. Okay. So, for this unique start time remains same, whatever the general case, it will remain as it is, right. So, next one was the precedence constant or data dependency. So, if you remember that if there is an edge from Vj to Vi and this node has a delay of Dj, then what is the idea that if this is scheduled in Tj and it will take say till Tj plus Dj minus 1, right. So, it will execute in this time step. So, the Ti, the time step of this Ti must be greater than equal to Tj plus Dj, right, that we have understood, and we can represent this Tj this Ti by this and Tj by this, because I have to represent everything in terms of Xij, Xil, and so I just rewrite this expression like this, right, in general case. So, what is the difference here? So, in general case this node can have a delay of Dj, but in our specific multiprocessor scheduling my Dj is equal to 1 for all nodes, right, for all I or for all j 1 to n, right. So, since this is 1, so I have to just rewrite this by this and I can get this expression. So, for multiprocessor scheduling my data dependency constant will be this instead of this. Okay. So, this is the correlation, understood. So, now I will move on to the next constant. The next constant was the resource constant, you remember, and the resource constant says that in each timestamp the number of operations that are running in that timestamp offset one type of resource k must be less than ak, right. That means the number of resource available of type k. So, I have to identify the number of operations that are running in the timestamp L, and I have to say what is their type. If their type is k, I will only take those operations which are type k. I have to make sure that the number of such running operations must be less than of the resource bound of type k, right, and that was given by this expression, I hope you remember. So, this actually identify the operations that are running in timestamp L, and this actually give me the things which is of type k. So, this is basically gives me the things, the operations that are running in timestamp L of type k, and that must be less than or equal to a k, where this k will vary for all type of resource and L will vary for all time of timestamp. So, now how this two assumption will impact this particular expression. So, what was the assumption? You just to recall that I do not have different type of resource, I have only one type of resource. So, I do not have this k type of resource, I have only one, right. So, this will go, this I do not need, right, because this is it is basically one type of resource are there. And next was that here this is coming because we have to identify the operations that are running. It is basically identified by this expression, but since for my case it is basically my di equal to 1, right. So, the delay is 1 unit delay. So, this summation will become m equal to so this L minus 1 plus 1. So, m equal to L to L. So, which is that this summation is not there, right. So, it is basically x I L, right. So, basically what does it mean? It is basically this the operations that are L to L, that means this is the all the operations that are running in a timestamp, right. So, what just to summarize that here all type of, so all the nodes that are running in this time, right. So, it is basically x I L. So, I have to identify all the x I L which is 1 in this timestamp, and that must be less than or equal to a, right. So, this is how I this expression reduced to this expression, right, because I do not have to check for all type of resource, I do not have to identify the running operations, only the operation if it is scheduled in this timestamp. So, all the operations that are scheduled in this operation in a timestamp L, that must be less than or equal to the total resource bound, because I have only one resource bound, because this I have only one type of operations, right. So, this is how this will move. This objective function will remain same because it is a minimization of the latency. Okay. So, this is how I can actually formulate this multiprocessor scheduling as an ILP, where my objective function as it as the general case, unique start time won't change, it is the same constant, data dependency constant all same, only this delay will be replaced by 1, and this resource constant is be simplified because here there is no running operation concept, because this all operations are of unit delay. And what we have to just check, the all operations that actually schedule in a particular timestamp must be less than of the resource bound of that state, right, that is given by this. So, let me take the same example, since the resource constant does not change, it will remain as it is, right. So, this is sorry unique start time constant does not change, whatever was for generic case it will remain as it is. I will just explain one of them, say. So, let us say take me this 8. So, since this if I am assuming this is actually going to be scheduled in say 4 timestamp, right. So, 1, 2, 3, 4. So, this even if it come here or here, the total timestamp won't differ, right. So, similarly, if this operation comes here, this operation comes here. If this operation comes here, this operation can be scheduled come here. So, that means this 8 can schedule either timestamp 1, 2 or 3, and 9 can schedule. So, this is V 8, and 9 can schedule either in timestamp 2, 3 or 4, right. So, I have to say that this 8 schedule either in timestamp 1, 2 or 3, but it can schedule only one of the timestamp, right, that is given by this. Similarly, 9 is something either 2, 3 or 4, but only one of them, it can schedule only one of the timestamp, right. This is how I can actually identify the unique start time constant for this ILP formulation. For the precedence constant, it is basically for every edge, right. So, if you just take an edge here, so this is I have to check the possible start time of this and the possible start time of this, but the difference will be 1, right, because this operation has a delay 1 now. So, what are the possible start time of this node, say 7. So, let me take this example. So, 7 can start here or here without touching the delay, and if 7 works here, the 6 can come here. If 7 schedule here, 6 has to schedule here, right. So, then So, this is the possibility of the timestamp where 7 schedule either in timestamp 2 or timestamp 3. So, if it is scheduled in timestamp 1, this will be 1, right, this will be 1. So, it will become 2 and this will be 0. So, this will say 2. If it is scheduled in timestamp 3, so this will be 1 and this will be 0. So, it will effectively means 3. Right. So, this is how I can define the timestamp of the start time of the node 7, and this is actually given the start time of the node 6. It is either in timestamp 1 or timestamp 2, and it is saying that and it is the delay of the node 7. So, start time of 6 must be, start time of 7 must be the start time of this node plus 1, right. This is what this expression says. So, now I have to take each such edge and I have to represent them using the constant. And the only difference from the generic case, here it is basically D6. In previous case it was D6, here it is just 1, right. So, that is the only difference from the generic case. And for resource constant is basically I have to see what are the node that can be scheduled in timestamp 1, because so what are the node can schedule in timestamp 1. So, 1, 2, 6, 8 and 10, right. So, that means x 1 1 plus x 2 1 plus x 6 1 plus x 8 1 plus x 10 1 should be less than equal to t. It should be less than equal to a, because this a is the resource bound. I have one type of resource, right. And for timestamp 2, so if you now just think about the timestamp 2, so obviously 3 can schedule 7, 9, 11, and also I have told you that this can come here and that time 6 can come here. 6 also can schedule in timestamp 2, 8 also can schedule in the timestamp 2, 10 also can schedule, right. So, I have to write x 3 2 plus x 6 2 plus x 7 2 plus x 8 2 plus x 9 2 plus x 10 2 plus x 11 2 should be less than equal to a. So, there are many operations which is actually likely to be scheduled in timestamp 2, 1, 2, 3, 4, 5, 6, 7 operations, right, can be scheduled, but only if say a equal to 2, only 2 of them can get scheduled in timestamp 2. Okay. So, this is how I have to write constant, resource constant for each timestamp. This is for 1, this is timestamp 2, this is for timestamp 3, this is for timestamp 4. I have to write such operations. Okay. So, this talks about the resource constant. So, if I just give this constant 3 constant and with that objective function, it will actually give me a solution which is actually minimize the latency, because my objective is to minimize the latency under a given resource constant a, and since I have only one type of resource, I have only one resource bound. Okay. So, this is what is this problem, and this is the ILP formulation. Okay. I hope you understand. So, as I mentioned in the start of the class that the objective of this class to identify a subclass of my sequence graph which is polynomial time solvable, right. And if we assume this, the graph has all operations of same type, that there is no different types that I have already assumed, and the all operations have unit delay, still this problem is NP complete, right. So, even if this this particular two assumptions are there, still these problems are NP complete. So, as I mentioned, this types are there are 4 characteristics I have considered. One is the DAG, which is always true, it is always true, and then it is a tree or graph, and then the third characteristic was the delay. The node delay can be many things, and the type of operation. So, what we have taken this is, so I have assumed that this is saying the type of operation. So, this A1 assumption 1 saying that I have only one type of operations, one type, right, and this delay. So, this A2, so A2 actually restrict this delay also, so that the delay is also 1, right, for all nodes. But still, even if this assumption was taken and this this sequence graph can be graph, the sequence graph can be a graph, then still the problem is NP complete. Now, if you assume the third assumption, right, I am assuming that this particular graph is a tree. Okay, it is not a this sequence graph is not a graph, rather it is a tree. So, that means there is a unique path from each node to the sync node. Under these 3 assumptions, this problem turns out to be is in P. that means it is a polynomial time solvable. So that means I have a efficient algorithm which will be complexity of n to the power k, where k is some constant with these 3 assumptions. Okay. So, this is very important, right. So, when we actually assume these 3 A1, A2 and A3, then I have this problem become P and I have exact solution in polynomial time. Right, and I can actually come up with some greedy strategy to solve this problem. So, let us try to understand why this, after once we assume this is 3, why this problem become easy, right. So, let us try to understand I am not going to prove it, but I am just going to give you some intuition about that. So, the point here is that, so because when you try to do the scheduling, you will start from say start step 1, right. You try to schedule the timestamp 1, then 2 and 3, right. So, when you try to take a decision at timestamp 1, if you have, you can actually take a greedy strategy that if I take this node to be scheduled here, that will give you the best solution, then it's this greedy strategy works, right. And for tree, this greedy strategy works. Why? So, this is because of this property. So, if you just think about a single path from any vertex to the sink node, you can actually have a monotonically unit-wise decreasing level, which is basically the path length. You can see here, if you just think about this this graph now, in this graph. So, if you just take a path, if you think the length of this the node have some level which is say 0 here, and the length distance from the sink node is 1, for this node is 2, this is 3 and this is 4. So, this is the length of the path and this is monotonically increasing, right. So, you can think about, so you just take any path, here I am also giving this is the this is 1, this is 2. So, because of that, so when are you actually taking this node, because at the time step you are going to take the node which has predecessors or input, right. So, among these nodes you see here the delay is 4, for this node it is 4, this is 3, this is 2, this is 2. So, you can actually choose, because so if you if the distance is more, that means it has more operation to be scheduled in the subsequent part. So, you can definitely, if you have a resource bound is 2, you must take these 2 nodes, right, because that has the maximum criticality, in the sense that the distance from this node to the sink node is maximum. So, that is something. So, that since there is a unique path from each node, so there is always this value is always unique, and you can actually take a greedy strategy that at this point, if I have 2 resources available, I must schedule this node with level highest level. Okay. So, this kind of greedy strategy will works, and I can actually take a local decision without looking into the other part of the circuit, because and that actually ensures that it is the best decision, right. Whereas, you think about this kind of graph, right. So, here you see here there are a lot of paths and the distance of the paths are many, right. For example, if you just think about this in this graph, there is a path from here which is 1, what is the distance 1, 2, 3, 4, 5, 6, 7. There is another path from this node which is like this. So, 1, 2, 3, 4, 5, 6, right. So, if you think about this node which is basically of, so if you think about this path which is delay 1, 2, 3, 4, right. So, from this node to this node there are many paths, 24 paths are there. Some of the delay node paths has delay 7, some of the path has delay 4, some of them is 5, 6 and everywhere, right. So, now the point, since there are many such nodes, so at this point it is not something your decision, some local decision at this point may turn out to be an incorrect decision, because you do not know the structure of the rest of the graph, right. Similarly, here, so suppose here you can see here from this node there are many paths, right. So, there is one path like this, there is one path like this. So, there are many paths and every path may have different delay. So, just taking a decision at this point, because of there are many paths of different not unique delay, your decision at the start, a greedy decision at the start may not be correct. So, that is why in general this is the intuitive idea that once you have a generic graph, your local decision won't work, you have to explore all possible choice, then only you can actually come up with the best solution. Whereas, for this graph which is basically special type of graph which is a tree, since all paths have unique, there is no such confusion. So, you can actually take a local decision and which actually give you the best solution. So, that is why once you have these 3 assumptions, this A1, A2 and A3, your problem become P and you can actually have a efficient solution. In next class, I am going to explain another one of the such algorithm which is called Hu's algorithm, which solve this problem in order of n time very fast when these 3 assumption holds for a sequence graph. Okay. So, with this I conclude today's class. Thank you.